it has a fundamental component, but it also has some harmonics. The same thing for this signal, the same thing for this signal. So what's the solution in order to reduce the harmonics? What did we do for single phase inverter? That's right, we used sinusoidal PWM, right? So instead of having just one cycle, we created more cycles, and we used comparators, and like that basically improved the harmonics and the quality of the current for our inverter. So like we are gonna do exactly the same thing here. So we're gonna have 3 different comparators. Okay, let me just like draw one. So again, the first topic, it's sinusoidal PWM. So like we're gonna have a sinusoid here, and the other signal, it's gonna be maybe I'll do this one. The frequency of carrier has to be higher, right? So let's say like we have something like this, and this would create the gating for phase A 1 upper, and we give the inverted version of that to 1L. Okay, so this is for phase A. For phase B and C, we do exactly the same thing. Let me just erase this part. We do exactly the same thing. We use the same carrier sawtooth waveform or triangular waveform, exactly the same thing. But our sine waveform, it's gonna have a phase shift. How much is that phase shift? Yes, 120 degrees, because we want phase A and B to have 120 degrees phase shift, right? So let's say like if I want to do 120 degrees, it's just gonna start from here. So it's gonna be something like that. Okay. And this is gonna be the gating voltage for 2 upper switch, and the inverted would go to 2L. And finally, this is gonna be the phase C, or sorry, 3U and 3L. Again, we use the same triangular waveform, and our sinusoidal input, it's gonna have 240 degrees phase shift compared to this one, or 120 degrees phase shift compared to this one. So if I want to draw this, it's gonna look like something like this. Okay, so 120 degrees, 120 degrees. Okay, and if we do that, again, we have the same concept for sinusoidal PWM. We want to have the frequency of the carrier signal high enough so that we don't have like a huge harmonic component. But at the same time, you have to know that this is a trade-off. As you increase the frequency of the switching, you would have more switching losses, right? It was very hard for me to draw the 3-phase waveform. So if you look at what Dr. Jeff prepared for us, let me see if you guys can see this. Maybe I can just bring this a little bit closer. So Dr. Jeff actually prepared this for us. This is page 18 of your notes. You would see that this is what we have for phase voltages, right? The phase voltages in here, like this is VAN, VBN, VCN. They switch between VD/2 and negative VD/2, right? And this is created by comparing the sinusoid, which is this sinusoid, with a triangular waveform. And this one, the sinusoid is 120 degrees phase shifted. but with the same carrier signal. This is what we have for VBN, and this is for VCN. And if you look at the line-to-line voltages, VAB, VAC, and VBC, this is what we end up with. And this is actually like satisfying what we want. We have a periodic signal, which is like pulse width modulated square wave. It has the fundamental component, but in addition to that, it has some harmonics. If you increase the frequency of switching, the frequency of the carrier signal, you would have less harmonics. But as I mentioned, it's a trade-off. You would have more switching losses. So this is something that you have to consider. Okay. So here, like there's like again, like you have to be careful about the modulation index. You don't want to have the amplitude of the sine signal to be higher than the carrier signal, because that would cause overmodulation, right? So MA, you want to keep it less than 1. And MF, the higher the higher the MF is, we would have less harmonics. One concept that we have in 3-phase inverters is that if our MF, let me erase this one. If our MF is a triplet number, means like if it's a multiple of 3, all the odd triplet harmonics will get cancelled. So this is also mentioned in Dr. Jeff's notes, will get cancelled. What do I mean by odd triplets? It means like 1 times 3, so 3rd order harmonic. 3 times 3 means 9th order harmonic. 5 times 3, 15th order harmonic, right? So by also adjusting MF in this case, if you write the Fourier transform for the PWM signal, you will see that these harmonics get cancelled out. You still need like filters, for example, for the, because we still have like, this is like 3, this is 9, this is 15. So it means that we still have 5th order harmonic, 7th order harmonic, 11th order harmonic, 13th order harmonic. So if you want to cancel those, you still need to have a passive filter, an LC filter. We also still have the same thing that we mentioned for the single phase inverter. The even order harmonics, they are cancelled out. Like ideally, like their value would be 0. In practice, it's going to be very small, so we don't have to worry about that. So this is all I wanted to share with you about 3-phase inverters.